When we talk about buffers, there are two important properties of buffers that we must consider before we even think of preparing a buffer. So the first of these is what we call the buffer range. So buffer range is defined as the pH range over which a buffer effectively neutralizes acids and bases and maintains a fairly constant pH. So let's divide the two parts of the definition. Okay? The first part is a buffer range is a pH range. So it's a range of pH values over which a buffer is effective in neutralizing or countering the effect of an added acid or base. Okay, now the second part of the definition is that it is a pH range over which the pH is maintained. So you have a fairly constant pH. So you recall I mentioned that a drastic change in pH should be a change by 1 unit. So a change from pH 6 to pH 7 is already considered drastic. But if we say from pH 6 to pH 6.71, that's not yet drastic, and we are still maintaining a fairly constant pH, that means the buffer is still effective. Okay, now let's talk about this buffer range. How do we determine the buffer range for a certain buffer solution? We go back to our Henderson-Hassleback equation and recall the diagram I showed in a previous video of how a buffer system works. Okay, so first, do you remember in that diagram, we started with an equal amount of the weak acid and its conjugate base? So if we use the Henderson-Hassleback equation and consider that we have equal concentrations of the weak acid and the conjugate base, what will happen to our equation? So if these two are equal, then this ratio is equal to 1. So we have pH equals pKa plus logarithm 1. But what is the value of logarithm 1? It's 0, right? So if we have a buffer with equal concentrations of the conjugate base and the weak acid, then we expect that the pH of that solution is just equal to the pKa of the weak acid. Now, what if, okay, so let me just take note of that. If the concentration of the conjugate base is equal to the concentration of the acid, pH is equal to pKa. Now, what if, let's say, the amount of conjugate base is 10 times that of the acid. So the concentration of the conjugate base is 10 times the concentration of the weak acid component. What happens now is that we have a ratio that is equal to 10. So we replace the concentration of the conjugate base with 10 times the concentration of the acid, and we can cancel out the concentration of the acid, and we are left with logarithm of 10. And what is the value of logarithm of 10? It's equal to 1. So we see that if the concentration of the conjugate base is 10 times the concentration of the acid, our pH now is 1 plus the value of the pKa. So let's take note of that. If the concentration of the conjugate base is 10 times the concentration of the acid, the pH of the buffer solution increases by 1, okay, relative to the value of the pKa. Now, we can also consider another scenario. So the scenario is, this time it's the concentration of the acid that is 10 times the concentration of the conjugate base. So what happens is, you have an acid that has a higher concentration than that of the conjugate base. So we can cancel this out. And now the ratio is 1 over 10 or 0.1. And logarithm of 0.1 is equal to negative 1. So in this case, if the concentration of the acid is 10 times the concentration of the conjugate base, we see that the pH of the solution also changes by a value of 1 unit, but this time it decreases. Okay, now we see that we saw in our diagram that a buffer is very effective if it has equal concentrations of the two components. So this is actually the ideal case, that you have an equal amount of your conjugate base and your acid, meaning a very effective buffer has a pH equal to the pKa of the weak acid component, right? But if we try to increase the concentration of the conjugate base, of course, the pH will slowly increase, right? Because we are increasing the basic component. Up to a point at which the concentration of the conjugate base is 10 times that of the acid. So we have a lot of conjugate base versus the weak acid. The pH now changes by 1 unit, and we don't want that. We actually don't want to for the pH to change by more than 1 unit. And the same goes vice versa. If we increase the amount of the weak acid component, the pH will slowly decrease because we are adding the weak acid, but we don't want the pH to change by more than 1 unit. And this will happen if you have too much of the acid. Okay? So, what is the perfect buffer range? This pH range is defined as, so your buffer range is pKa of the weak acid component of your buffer plus minus 1 unit. So for example, if we have a buffer composed of acetic acid and acetate, so the Ka of acetic acid is 1.8 times 10 raised to negative 5. If we get the pKa, that's negative logarithm of 1.8 times 10 to the negative 5, it's equal to 4.74. This means that the buffer range for an acetic acid acetate buffer is 3.74 to 5.74, meaning it can maintain these pH values even if you add a strong acid or a strong base to the buffer. But if you have a mixture of the two and the pH is outside this range, you don't have a buffer. Okay?